Hello, hi everyone. Welcome back to the Temporal Graph Reading Group for the fall semester. Um, Today we are glad to host Louis, who will be presenting her recent work, Future Link Prediction Without Memory or Aggregation, with her collaborators from Renmin University of China. And so some speaker introduction. Louis is a PhD student at the Algo Lab, Renmin University of China, supervised by Prof. Zhe Wei. She received her Bachelor of Science degree in Computer Science and Technology from Beijing University of Post and Telecommunications in 2022. Her research interests include dynamic graph learning, multi-agent systems, graph unlearning, and efficient graph algorithms. She'll be visiting the University of Montreal from September 2025 for 6 months. Her homepage is listed on the website as well. So you are currently in Montreal.
Yes.
Okay, I think
Yeah.
we just missed each other.
Yeah.
I'm now in Oxford
Oh,
now, but I was
oh,
at Mila in August. But yeah.
oh, yeah. Sorry to hear the news. Yeah, I found that on your homepage that you are doing a post PhD in London, right?
Yeah, I'm doing a postdoc at Oxford right now. Yeah.
Oh,
So
yeah.
I'm currently in Oxford. Um, okay, so let's get started. I will hand the mic to you.
Yeah, thank you. Thank you for the kind introduction. Hello, everyone. Thank you for coming to my talk. I'm Lu Yi from Renmin University of China, and today I'll be presenting my work, Future Link Prediction Without Memory or Aggregation. This work has been just accepted by NeurIPS. Let's start from some background here. First, the topic we focus on temporal graphs. In temporal graphs, both nodes and edges evolve over time. For example, in social network, new users join in the network and form new connections. And in recommendation network, users purchase and review products at different times. So temporal graphs better capture these real-world dynamics compared to static graphs, which ignore the temporal evolution of relationship. And temporal graphs are generally categorized into two types, discrete time and continuous time. A discrete time temporal graph is a sequence of graph snapshot G1, G2 to GT, where each snapshot may include many new nodes and edges. And in contrast, a continuous time temporal graph is a stream of edges, each associated with a time step, capturing the continuous evolution of the graph over time. So temporal graphs can support various tasks, but in this work, we focus on future link prediction. The goal of future link prediction is to predict whether a link will form between two nodes in the future. Specifically, given a graph G, a source node S, a destination node D, and a prediction time T, and all edges before time T, the model is asked to predict the likelihood of the edge SD appearing at time t. So this problem is often framed as a ranking problem. So we ask the model to rank the positive target node D higher among sampled K negative target nodes. Now let's move on the motivation behind our work. Our previous study, TGB-SIG, has shown that existing methods excel in seen edge prediction, but struggle to generalize to unseen edges. Here, seen edges refers to edges that have already occurred previously before the prediction time. So there are two pieces of evidence for this. First, we evaluated existing temporal genes on both seen and unseen edges across various datasets, including Wikipedia and Reddit. In this figure, the performance of unseen edges is shown in shadow here. So from this figure, we can see that models perform significantly better on seen edges than on unseen edges. Second, we tested existing methods on future link prediction using two widely adopted recommendation datasets, Google Local and Movilence. All edges in these datasets are new, meaning that they did not occur before the prediction time. So since recommendation is a typical application of temporal GNNs, right? We expect these methods to perform well, similar to their performance on Wikipedia and Reddit. However, we observe substantial performance degradation on these two datasets. However, in real applications, unseen edge prediction are very common. For example, in e-commerce, we need to predict new products for users because users rarely buy the same product repeatedly. And in citation network, if a scholar wants to explore new collaborations, we need to recommend new co-authors rather than authors they already know. Yeah. So this limitation will hinder the application of existing methods, especially in scenarios where predicting unseen edges is crucial. In our prior study, TGB-SIG, we proposed a new benchmark to emphasize unseen edge prediction and to inspire the development of new methods. Another aspect we observe is that most existing methods typically adopt two modules, memory module and aggregation module. The memory module, often implemented with RNs, uh, it aims to it aims to compress the interaction history in a latent vector. And the aggregation module implemented by Transformer, NLP Mixer, or other models. It aims to aggregate historical neighbors. So this observation raises two important questions. First, how can we design a model for both seen and unseen edge prediction? And the second one, are memory and aggregation module truly effective for future link prediction? Note that most existing methods rely on these two modules, but they cannot handle unseen and seen edges simultaneously. So this casts doubt on whether these modules are truly effective in practice. So to address this, we propose Craft, a solution for both seen and unseen edge prediction. Let's first look at the overall architecture, and then we will dive into the details and the rationale behind our design. So Craft has two key components. First, the learnable node embeddings. It serves as unique node identifiers. And the second one, target-aware matching, which is implemented by cross-attention between the source nodes and the source node's neighbors and the target node. So first, let's focus on node embeddings. For each node, we assign a learnable node embedding E, and we also define positional encoding, P. And for the neighbors of the source node, we will combine the node embedding E and the positional encoding P to derive the final representation. So why do we need the positional encoding? This is because recent neighbors reflects recent interests. So positional encoding here helps capture the temporal order of interactions. So, and for target node, we use the embedding directly.
Uh, just some clarification.
Yeah.
So what exactly is the learnable node embeddings?
So it is a learnable vector, and it serves as the node identifiers just like the feature, but the feature is static. It will not change, right, during our training.
Right?
But yeah, but the embedding will change by the gradient descent during training.
But what's the input to this node embeddings module?
The input is the ID, just like node one, node two. Yeah, the numerous
Oh,
ID. Yeah.
it's just node ID, okay. And the positional encoding is
The positional encoding, the its input is the index of the neighbor in the sequence of the source node's neighbors. For example, the most recent neighbor, it can be the first neighbor, and the second neighbor will be the second latest neighbor will be the second neighbor. Yeah. So it input the first, second, the index, and it will turn to output learnable embedding two.
Okay, so sorry for so many questions, but how do you still model the edges?
Sorry?
How do you model the edges? This is just for the node itself.
Yes. The modeling of edges will in the next page.
Okay,
Yeah,
okay, okay, okay. Sure. Thanks.
yeah. Okay, let's continue. Mm. So before the modeling of edges, I want to clarify why do we need learnable embeddings. So in previous methods, we do not use learnable embedding, but use the node feature as node identifiers. So it will solely depend on node features, but features are often missing in real-world datasets. This is mainly because features are hard to collect or very expensive to collect in real-world applications. And it is difficult to align across different types of nodes. So without the features or the features are all zeros vector, the existing methods cannot distinguish nodes. For example, takes this little graph as an example. We want to predict whether the node B will interact with A or F at time 4. However, when no features are available, A and F appear identically because they both have interaction at time 1 and time 2. So as the node F interact at time 1 and time 2. So previous methods cannot differentiate between A and F. So this highlights the need for a unique node identifier for modeling power. So learnable embeddings solve this problem. So each node embedding is learned from the node's interaction history. Naturally, give the node a unique representation and also allowing the model to capture the node's specific patterns effectively. Yeah, that's the rationale behind our learnable embeddings. And we continue with the second part. After we obtain the node representation, we apply a cross attention between the source neighbors and target. Specifically, we will define Q, the query, as the target node representation and the key and value as the sequence of source node neighbors. So we then feed this into the standard transformer encoder, and the L layer cross attention module will output the representation of the potential edge SD at the prediction time T. So at this, by this, we will derive our representation of the prediction edge. Yeah. Mm,
Um,
let's,
yeah,
yeah. Mm,
sorry, can you go through a little bit more detail? So you look at K recent neighbors. So I
yes.
assume one hop,
Yes, both are one hop.
right?
K historical neighbors. Yes.
You generate the node embeddings as input to the transformer.
Yes. For the neighbors of the source node, we will add the positional encoding. They will combine into the final representation. But for the target nodes, we will directly use the learnable node embedding. So this part will be the query, and this part will be the key and value. Yeah.
What's the reason to make the source destination different? Because we want to predict the destination.
Um, yeah. So this is because we cannot identify the index for the destination, right? So
Mm-hmm.
it is there are no positional encoding for them because they have no order. And we add positional encoding here just because the neighbors of the source node has order, and
Mm-hmm.
the most recent neighbors indicates the most recent interest of the source node. So there are no positional encoding for the targets, but only for the source node's neighbors.
Okay, so some of the target, which is never neighbor of the source node, will get basically zero vectors.
Yeah, yeah. Mm.
Okay, I see. Okay, thanks.
Yeah, let's continue with the rationale behind target-aware matching. This is one of the key components of our craft. So let's compare it with other matching approaches. So the first one, independent matching, which is adopted by most existing methods. In the independent matching, we model each node independently. For example, in this example, there are user A. User A has purchased iPhone, AirPods, and iPad. So we will model user A by itself and its neighborhood. And we want to predict whether user A will purchase iPhone case. Then we will model iPhone case independently by its previous purchaser, that is user B and user C have purchased iPhone case. So we model iPhone case by this little neighborhood. So in the case of independent matching, we model each node independently and neglect the relationship between the source and the destination. So the second one is neighborhood matching. In this matching style is adopted by Digiformer. In Digiformer, it models the relationship between the neighborhoods of the source node and the destination node. So it will perform a self-attention among the sequence of the user's A's neighbors here and append the iPhone case neighbors here. So it will do a self-attention on this sequence. So neighborhood matching will introduce some cross-node awareness, right? But when the source and target neighborhoods lack semantic overlap, or they are of different types, the attention signal can be misaligned. For example, in our case, user B and user C may purchase many other products, so their representation may not align well with the target iPhone case. So as a result, this approach cannot fully capture the compatibility between the target and the source context. That is, it cannot capture the relationship between the iPhone case and the source, the source node, the user A's previous interaction history. So in contrast, we adopt target-aware matching. It allows the target node to directly attend to the historical neighbors. In our example, iPhone case will attend directly to iPhone, leading to a very intense attention between them. So this produces precise and meaningful attention signals, helping the model to capture the relationship between iPhone case and iPhone. Yeah, that's the rationale behind why we design target-aware matching.
Yeah, makes sense. So does target-aware matching also include user A, or doesn't really include user A in the matching process?
Oh no, it will not include the user A, right? In just depicted in this figure. So only the user's A's neighbors, that is what products if user A purchase will appear in our model.
Mm-hmm. Right.
Yeah.
Okay,
Mm.
thanks.
Let's continue. So let's move on the third part of our architecture. After obtaining the edge representation from the target-aware cross-attention, we will append two additional features. First, the elapsed time encoding. The elapsed time is the time since the target's last activity. So this is used to capture the temporal status of the target node. And on scene-dominant datasets, that is, the datasets contain many extensive scene edges. So in this datasets, we will append the repeat time encoding. The repeat time counts how many times the edge occurred before the prediction time. So both these two encoding will be implemented using a linear layer. So that's all of our architecture. If you have any question, you can raise now or after we finish the experimental result. That's all okay. Okay, now let's move on the experimental result. First, we will look at the unseen dominant datasets. This group includes most datasets from TGB-SIG plus 2 from TGBL. In this dataset, the repeat ratio is less than 30%. So from this table, craft outperforms all existing methods. And on 6 out of 9 datasets, it gives about a 10% relative improvements. And the gains are especially large on wavelengths. Here, 50%, and on flicker, about 25%. Next, let's check the scene-dominant datasets. On these datasets, we use CRAF-R, which is we will add the repeat time encoding in the CRAF. So CRAF-R achieves 10% relative improvements on 50% datasets here. And the improvements are strong on MOOC here, around 47%, and on TGBL flights, 29%. So,
Um,
yeah,
just a small question. What is the batch size you use?
batch size. Oh, yeah. So the batch size we use follow existing methods in all these data sets. We use batch size of 200, and
Okay.
in the in TGB-SIG data sets, because we use a batch size of 400 in our TGB-SIG paper, so we follow the setting there and use batch size of 400. But this is aligned across all methods. Yeah.
Okay. That's good. Thanks.
Yeah, let's talk about inference time. In terms of speed, Graph is faster than all other methods. These figures show the inference time over the flights, Yelp, and Wikilink. And we measure the total inference time over the test set of these three datasets. So in every dataset, Graph is the fastest with a big gap to the baselines. For example, in the Wikilink, one of the largest dataset, Graph needs only half the time of DIREP, and DIREP was already the fastest among these baselines. So these results demonstrate the superior efficiency of Craft. Next, we validate the two key components, learnable embedding and target-aware matching, which are our key components of our craft. So to test their impact, we replace the feature in TGAT and digiformer with our learnable embeddings. So TGAT with learnable embedding, which we call TGAT-LE, performs much better than the original TGAT. And digiformer LE also improves, outperforming the original digiformer. But remember, TGAT uses independent matching, and digiformer uses neighborhood matching, and our craft uses target-aware matching. So the results turn out that craft outperforms DJT LE and digiformer LE. So this validates the importance of the target-aware matching. finally part the abbreviation study. We study on positional encoding, elapsed time encoding, and repeat time encoding. And we showed results on Wikipedia, MOOC, UCI, TGBL Review, and Google Local. The results show that all three encoding help, but their improvements varies across datasets. So in Wikipedia and UCI, the repeat time encoding is crucial. This is because these datasets have many repeated edges. And on TGBL Review, Wikipedia, and Google Local, elapsed time encoding is important since the popularity is crucial in these cases. And on MOOC and Google Local, positional encoding plays the biggest role. So overall, all encodings are useful, but their impact depends on the dataset. Yeah, that concludes my talk. To summarize, we revisit the memory and aggregation module in previous methods, and we identified two key modeling requirements. First, the unique node identifiers, and the second one, target-aware matching. And we implemented these requirements with two components, learnable node embeddings and cross attention between the target node and the neighbors of the source node. Yeah, so Craft achieve with these two components, it achieves superior performance on both seen and unseen edge prediction. So in this way, it overcomes the major limitation of previous methods. Thank you all for your attention, and that's all I have for today. I'd be happy to take any question now.
Great. Thanks for the great talk. If there's any question from the audience, feel free to type in the chat or just unmute yourself to ask questions. Um, yeah, yeah, thanks for the talk. It's actually very clear and nice. Um,
Thank you.
I wonder, so the architecture is obviously very specialized for link prediction tasks and works very well, right? I
Yes.
wonder if you have tried to use it for, I mean, how would you extend this to node level task or graph level task?
Yeah, so I think it is specific for future link prediction because we will derive the edge representation for each potential edge. Um, it is
Right.
unlike Yeah, it is unlike previous methods. It will model each node independently and use MLP to uh, output the probability of the edges. So it is specific to future to link prediction problem.
So which means that for any given node, you have to make at most n predictions if you want to predict for every single edge that node can possibly have. Because you generate an edge specific embedding, right?
Yes, yes. So it is for edge specific problems. So if we want to do node level problems, so I think node representation is needed.
You could, I mean, you could by just look at the neighbors of the node and you do a pooling over the edge embeddings you have here over this node's past neighbors, and you generate a node embedding and you can feed it for node level task.
Oh yeah. Do you mean we use the edge representation
Yes,
and do a pooling?
yes. So instead of you take the you do the edge representation for the edges that most of them don't exist because you are ranking them, right? So now you only look at the edge embeddings for the actual neighbors of the node, and
Yeah,
then you
yeah.
pull over these
Yes.
edges, and
Yeah,
then
that's
you have one embedding, and you can try with node task.
yeah, that's a promising method, I think.
Hmm. Yeah, I'm just curious because it seemed to do really well for link level task. And also, I'm slightly concerned about multi-hop. So I know that for link prediction, you really don't need a lot of multi-hop, which I
Yes.
understand. Uh,
Mm,
but potentially there might be some specific case where multi-hop might be helpful, especially
yeah.
as you move more towards node level representation or subgraph level representation. Um,
Yes. Mm,
yeah, but it's not very straightforward to add. Like here, you can add all the two hop neighbors as well. But the the amount
yeah.
of stuff you are doing attention over will kind of start to explode.
Yeah, for multi-hop neighbors, I think we can also add the multi-hop neighbors, just like here. Let's be append multi-hop neighbors
Yeah.
to the sequence of the neighbors. It is also a way, but I'm not sure how good it will be. Yeah. Mm.
Yeah, but your cross attention is gonna explode, right? Because two hop you
Yes,
have basically,
yes,
quadratic to the number
yes,
of neighbors. Yeah. Um,
yes. So, yeah. Mm.
yeah, yeah, sorry, you were saying?
Yeah, I think this method is very specific to link prediction. So I think it will be a future direction that we have to design specific methods for different tasks. It will work better than we design a general methods, right? Like self-supervised method that it can use one node representation for all tasks. I think the specific methods will definitely will be better, but it will sacrifice some generalization. Yeah,
Yeah, but yes, I agree with that to a certain extent.
yeah,
Um, but also technically the idea you present here can be applied. I mean, you have tried in your experiments to apply to different models, right? You just need to do a bit of task variation on your model,
yeah, yeah.
kind
I
of.
think it's promising. Yeah.
Yeah, sounds good. Are there any questions from the audience? Feel free to type. I have a final question I want to ask. So it's not directly related to the paper, kind of, but not directly. So I don't know if you are aware, but we have built a new machine learning library for temporal graph. It's
Yeah.
called TGM. So basically, it's a library. So basically, we're looking to include as many method because, as you know, you run the
Oh, great.
experiments. The current library are not the best. Let's just put it that way. So
Oh,
if
yeah.
you can take a look, yeah, when you get time, you can take a look here. We'll announce a public beta soon in a few weeks, and I think it
Great.
will be good to add this method. It shouldn't be that complicated to add as well.
Yeah, yeah. It's very
Because all you need is the recency neighbor information, and then it's just how you feed to the model, right?
yes, yes, yes. Great. I'll have a look at the TGM, right? Mm.
Yeah, TGM. You can take a look there. We
Uh,
already have like digiformer and TGAT and a lot of other things implemented there. Also, we have both CTDG and DTDG method there. So
great, great. Yeah.
so you can play around and let us know. Yeah.
Yeah,
Um,
it's a great direction.
and
Yeah,
also
I
potentially also for your prior work. So we natively support TGB, but potentially
yeah.
we can add some
Mm.
data processing for the TGB sequential data sets as well. So people can just do one line to get the data set.
Yeah, yeah. Thank you so much. Yeah, we previously used the DYG lib.
Yeah,
Yeah.
the digilib, yeah,
Yeah, yeah, but I think it can be better. Yeah, it is not as not very efficient, right? Yeah.
yes,
Mm.
yes. So yeah, so take a look and then yeah, so let me know if you wanna yeah, add it to the library or something.
Thank you, thank
Um,
you, thank you for
and
letting.
yeah,
Mm.
so thanks for presenting the paper
Yeah.
today. And yeah, so let's thank the speaker. So I have the recording from my end, so we'll have the recording uploaded at a later date. And
Thank you.
enjoy your stay in Montreal.
Yeah, thank you. Thank you so
Thank you.
much.
Yeah,
Yeah, thank you. Thank you
thank
for
you.
the nice
Yeah,
section. And thank you all for coming. Yeah.
yeah. Thank you. Bye, everyone.
Bye.
Bye.